look at analog modulation capabilities of the UTS3000A. The signal generator sends out an amplitude modulation signal. The base wave is a sine wave of 60 megahertz and a modulated wave of 1 megahertz. Turn on the output channel. Back to signal analyzers. In the mode, switch the working mode to analog demodulation. Inside the measurement, we find the amplitude modulation in the frequency menu. Change the center frequency to 60 megahertz. Set the span width to 3 megahertz. In this case, we can see the frequency domain plot of the AM signal in the RF spectrum window. Now let's set the span width to 5 megahertz. In the AF spectrum window, it is displayed as modulated wave because our modulation wave is set to 1 megahertz. Let's set the AF stop frequency to 3 megahertz. In the BW menu, set a value greater than 2 megahertz. On the RF spectrum, the green window lines is the passing bandwidth. Once tuned, you can see the frequency domain map of the modulation wave. The demod waveform window displays a time domain plot of the modulation wave. In the sweep menu, we have turned the scale time down. This makes the waveform clearer. In the amp menu, adjust amplitude to the appropriate size. In the AM mod depth window, we can see the data comes out of the analyst. Here you can see that the modulation depth is around 20%. The modulation wave frequency is 1 megahertz, and the other modulation analyst data. We can also turn on the peak function to locate the frequency and amplitude of the carrier signal, and also the frequency and amplitude of the modulated wave. Let's change the AM modulation depth to 50%. As you can see, the analyst data changes with it. Let's look at the frequency modulation analysis and analog demodulation. First, let the signal generator send out a modulation signal with a base of 60 MHz, a modulated wave of 1 MHz, and a frequency offset of 200 kHz. Let's go back to the UTS3000A screen. Set the mode to Analog Modulation Analysis, or Analog Demod. In the measurement menu, select FM Modulation. Open Frequency menu. Set the center frequency to 60 MHz. On the RF spectrum, the green window lines is the passing bandwidth. Set the span to 5 MHz. In this case, we can see the frequency domain plot of the FM signal in the RF spectrum window. AF stop frequency set to greater than 1 MHz. Now there is nothing in the modulation window wave. The reason is that we set the wrong channel bandwidth. Go to the PW menu. Adjust the resolution of the RF and AF window accordingly. Set the channel bandwidth to 3 MHz. The waveform is visible in the modulated wave window. Here we can adjust the reference level a bit to make the signal fully displayable in the AF spectrum window. Now the signal is fully displayed in the AF spectrum window. Adjust the demod waveform window. You can adjust the scale/division as necessary up or down to make the full waveform visible in the demod waveform, as shown here. Making the scale at 20 kHz is still not enough. Let's raise it to 100 kHz. Now you can see the full waveform in this viewing screen. Then go to the Sweep menu. Turn down the scan time. A clear, modulated waveform can be seen at this time. In the data window at the lower right corner, you can see the analyzed data, the frequency offset, the modulated wave information, and other data. Click on the window to zoom in. If needed, you can also use the peak function to quickly locate the peak information of the carrier and modulated waves. The UTS3080A series is a signal analyzer that can analyze IQ signals. Now let's look at its IQ analysis mode. Let's use the signal generator to send out a 60 MHz sine wave. Set the signal analyzer working mode to IQ analysis mode. What is the role of the IQ mode? IQ mode is capable of measuring both frequency and time domains. In normal spectrum analysis mode, it just scans the signal over frequency domain. IQ analysis usually uses the hardware chain of the entire spectrum analyzer. There is no excessive data processing such as a digital demodulation process. So, the IQ data is raw compared to the analysis data displayed on the screen of the spectrum analyzer, especially when analyzing a very complex modulated signal. The IQ data results can be exported. It is very helpful for the signal analysis. We can export the current trace or status as well as the measurement data. This is more often used to export measurement data. Why do we need to export measurement data? Because this measurement data is the rawest IQ data in the field of radio frequency. Both vector signal generation and vector signal analysis require raw IQ data. The exported data can be analyzed with our own mathematical analysis software or other softwares like MATLAB, or you can use this data to generate other data or signals. The upper window is the most basic spectrogram. The blue trace is the average trace. You can turn off the average trace in a measurement setting. The yellow trace is just a normal spectral trace. The average type can be voltage, power, or logarithmic power. Most of the time, we use logarithmic power averaging models. This window displays IQ waveform signal. That is the data we want. This purple trace is the I wave signal. The green trace is the Q wave signal. Because IQ analysis is used to test modulated signals. Let's turn on the modulation mode of the signal source first. Then we can see a modulated signal. The IQ waveform window shows the modulated wave. You can see it now. The modulated waveform is a sine wave. Now let's change the modulated wave to a square wave. You can see the IQ waveform is displayed as a square wave now. If you want to change the sweeping width to a little smaller, use the marker feature to mark it. You can see the details in the marker points. The values for the real and imaginary parts are displayed. Let's change trigger methods to single. Move the marker points to see the IQ corresponding value at each location. IQ analysis separates modulated waveforms into I path and Q path. These two signals can express the frequency, phase, and amplitude of the modulated wave. Let's go to the measurement menu. Choose to show only the IQ waveform window. Just look at the IQ waveform. Adjust the time scale and reference level to make the waveform appear clearly. In this example, we moved from 2 milliseconds to 30 microseconds. Also change the reference value from 0 to 10 dBm. So, what's the difference between IQ waveform and the one just tested before? Earlier, we separated the I and Q paths, but now here we see it as a modulated wave. This is the baseband signal in digital communication. It looks like a square wave. We can export the data by IQ to analyze it. You can also see the I and the Q paths of the modulated wave. Especially in the measurement spectrum, you can see how much the phase difference between I and Q channels is. Let's look at the phase modulation analysis and analog demodulation. First, let the signal generator send out a modulated signal with a base wave of 60 MHz and a modulated wave of 1 MHz and a phase offset of 180 degrees. Set the mode to analog modulation analysis, or DMOD. In the measurement menu, select PM modulation. As you can see, we're displaying 4 windows here. Make sure you select which window you want to change the values on, as each window has its own set of parameters, which is noted by a blue square around the window you currently have selected. Open the frequency menu. Set the center frequency to 60 MHz. Set the sweep width to 5 MHz. Set the AF stop frequency greater than 1 MHz. At this time, both the modulation signal and the modulated wave signal can clearly be displayed, so there is no need to adjust the BW menu. Let's adjust the DMOD waveform window. Adjust the scan scale to the appropriate value needed. The horizontal scale is also more appropriate. There is no need at this time to adjust the sweep menu. With the help of peak, we can see the peak information. In the data window in the lower right corner, you can see the data analyzed. Click on the window to zoom in. Let's look at the UTS3060A real-time spectral analysis capability. Let's look at the UTS3060A real-time spectral analysis capability. First, we need to switch testing modes to real-time spectral analysis mode. Then we can set up parameters and start a test. What is the difference between a real-time spectrum analyzer and a general spectrum analyzer? General spectrum analyzers process the data after a signal is received. When processing the data, the instrument will stop receiving a signal. In that case, it works like a DSO oscilloscope, so there will be a dormant time of measurement. With a real-time spectrum analyzer, the signals can be received and analyzed at the same time. The capture rate is high. It works like a UPO series oscilloscope. So, for the real-time spectrum, a POI, which means percentage of capturing probability indicator, will be used as a specification. In addition to this, real-time spectrum analyzers can also measure wider bandwidth and has a higher data analysis and receives triggering capabilities. It can also measure PVT, power versus time of a spectrum. PVT represents relationship between power and time. What is showing now on the screen is a density of signal spectrum. The longitudinal axis represents power. The horizontal axis is the frequency. These colors indicate the probability and number of occurrences. It means how often the signal appears at a relative frequency points. For the places that have no color, there is no signal at the frequency points. Red means highest probability and blue means lowest probability. So we use X, Y, and color to represent three-dimensional properties. In addition to spectrum density, you can also select normal in the measurement settings to monitor basic spectrum scanning. In addition to spectrum monitoring features in it, there's also a waterfall chart. Waterfall charts can display a record of all the signals measured in a history. We can look at every historical trace on top of the horizontal axis. It represents the probability of each occurrence. The darker the color is, the more frequently the signal will appear. The upper one is the older signal. The lower one is the latest acquired signal. The process starts from the bottom, so we see that waterfall chart scrolls from the bottom to the top. Let's take another look at the density of the spectrum. The upper graph is the density of the spectrum and the lower one is the waterfall chart. Then PVT is a power versus time relationship. The longitudinal axis represents power, the horizontal axis represents time. If I want to set up an amplitude modulation signal at the signal generator, I put this acquire time to the minimum. This gives you a logarithmic waveform. It shows the envelope signal of a modulated wave. This can be done in the amplitude settings. Change the display scale to linear. This shows that it is a sine wave. Let's take this modulation wave and change it to a square wave. Now it appears to be a square wave. Now let's change it back to a logarithmic scale. In addition to the above window display mode, let's look at the PVT spectrum. The window above is the power time analysis graph. Below is the spectrogram. We can also change its acquired time. Let it appear as an envelope of modulation wave. Here are a few ways to display the window. It's all about what we've covered earlier. Combination of windows. I won't go into details. In real-time spectrum analysis, the density spectrum is used the most. Now let's demonstrate the template triggering feature in the Scan menu. Select Frequency Task Trigger in the trigger type. Is it possible to set the frequency that we care about? First, we'll edit the trigger. Click the Edit menu to insert a row. Edit the template you want to set. The red line box is the mask for our editing, equivalent to zone triggering. If I change the mask condition, no signal that was past the red line will be triggered. Been waiting for the triggering. Change the mask to a value that can contain the signal. There is already a signal in the red zone. This can be triggered. It's more versatile. It's about testing something that is not easy to find or sporadic signals. The capture rate of the real-time spectrum is very, very high. Currently, the UTS3060A series, the 100% capture rate is 6.68 microseconds, meaning the signal needs to be greater than 6.68 microseconds. Then we can capture the signal at 100%. The UTS series comes standard with a vector network analysis feature. It is mainly used to test passive components or the reflection coefficient of an active device. Transmission coefficient tests require accessories such as calibrated parts and RF cable. At the mode menu, you can switch the working mode to VNA. Let's start with the S11 test. The DUT is a 1 GHz low-pass filter. Let's set the frequency range to be greater than 1 GHz. Here we set the center frequency to 1 GHz. The frequency range is set to 100 kHz to 2 GHz. Please note, calibration is required before testing. At the measurement setting menu, click calibration. There are 3 calibration steps. Let's connect the open circuit calibrator to an output port of the VNA. Click Open. After calibration, connect the short circuit calibration kit to the output port of the VNA. Then click Short. After calibration, connect the load calibration kit to the output port of the VNA. Then click Load. After the calibration is complete, the S11 is a 0 dB straight line. Connect the filter and the load to be measured. You can see the S11 curve of the filter. We can open 4 windows to display. In the Trace menu, select Trace 2 as the SWR and select Trace 3 as the Smith curve. Both curves are commonly used in S11 analysis. Now looking at the curve of Trace 2, you need to adjust the amplitude. Go to the Amp menu, click Auto Scale. The coordinate scale will be automatically adjusted. We can use the marker to mark the points of concern. For example, 1 GHz. At 1 GHz, the SWR is 1.14. A point can also be marked in the Smith diagram. The corresponding internal resistance and reactance can be seen. Let's look at the S21 test. Select S21 in the measurement. Because our DUT has not changed, the frequency does not need to be reset here. Calibration is also required before this measurement. The calibration of the S21 is a pass-through calibration. We access a pass-through connector between the two cables. Then click Pass-Through Calibration. After the calibration is complete, connect the filter between the two cables. The measured S21 curve can be seen on the screen. Let's look at the insertion loss with the marker. You can see at frequency ranges less than 1 GHz, the losses are low as a passband. At higher frequencies higher than 1 GHz, the S21 loss is high. Let's look at vector signal analysis. First, let the signal generator output the digital modulation signal of a QAM16. Switch the working mode to Vector Signal Analyzer. Because the frequency of the carrier wave of the signal source is 60 MHz, we set the center frequency of the VSA to 60 MHz. Then inside the measurement settings, set the modulation type to QAM16. Click on Measurement Setup. Set symbol rate to 1 MHz. The maximum measurement interval can be up to 4096. Let's set it to 256. The longer the length is, the more data that will be parsed, and the test will be slower. Go back to Frequency menu. Set the span width to a multiple of the number rate being tested. The larger the multiplier is, the more accurate the measurement can be achieved, but the data will be slower because the signal source is set to a block rate of 1 megabits per second. Here we set the bandwidth to 4 megahertz. In the upper right window is the symbol signal. The blue trace is a code symbol. It is the time domain signal. The red line is the position of the corresponding point of each symbol. Because when the vector signal was generated, it has a baseband signal. The real data that was sent is the symbol. Go to AMP menu. Adjust the reference level and scale to the appropriate values. The lower left corner is the constellation chart. The constellation chart represents different phases and different amplitudes, which shows how the signal that is characterized. The gray dot is a starting point. The red dot is the measurement point. The more it shakes, the greater the error is. The lower right corner is the signal received after demodulation and analysis. There's EVM, which means the vector amplitude error. It can be used to characterize the signal modulation quality. Theoretically, the smaller the EVM is, the better. Here is the amplitude error, phase error, as well as the frequency error. Also, how much IQ data has shifted. The last one is the quadrant error. The I and Q channels of the signal are orthogonal. With this parameter, we can see what exactly the orthogonal error is. In addition to the above forms of analysis, if needed, we can select other formats to view. You can view the I-way or the Q-way signal. You can view the IQ track. You can also view the I diagram of the I or Q path. The larger the I of the I diagram is, the better the signal quality is. Spectrogram traces can also be marked by marker dots or specific coded element points to analyze. Here you can see that we're using multiple marker dots. We're cycling between the different ones to give you pure examples of ways you can use these. Be sure to select which screen of the 4 screens shown here before selecting which marker dot you want to enable.